is a lousy woman, so at least I found someone to marry. Okay. Anyway, away from that. I remember last time we went as far as question 4. We just started question 5. I don't know whether we concluded with question 5 as I was cut off because of the network problems. I may seek guidance from the discussion crew.
I think we can start with 5.
May I seek guidance?
Yes, I think we can start with 5. It was not well concluded, so we can start with 5.
Oh, okay, all right. I think someone who is able to share, who is in the state of sharing, you can share the questions, the discussion kit. So we'll start from question 5. And now that it was a little bit touched, this makes our work easier today, and that we had solved it several times. So we're going to start from there. We see how we can work with it. The question reads, I'll read the question, and as someone is trying to share, I don't know our rescuer, who is that shares every day. Doc Moses or Doc Sidin, is it Sidin? Or Mr. Sidin, would you share so that people can see the question? In an electrolysis experiment, a student passes the same quantity of electricity through two electrolytic cells. Okay. One containing a silver salt and the other a gold salt. Over a certain period of time, she finds that 2.64 of silver and 1.61 grams of gold are deposited at the cathodes. What is the oxidation state of gold in the gold salt? So that is question 5 we're looking at. Okay. The panorama is open. Anyone to take on this question so that we see how we can go about it. Are we there, ladies and gentlemen? On question 5. So we are taught to find the oxidation state of gold if at all the same current was passed through this electrolysis, and we have 2.64 grams of silver being deposited and 1.61 grams of silver also deposited on the cathode, and we're told to find the oxidation state of these two. How do we go about it? Any ideas? So we should be mindful of the time. This is the 16 past the hour, so by 10 past the hour again we need to stop our discussion. That is 22:10. I don't know what time you, but by that time we'll be done because we only have 2 questions. Anyone who's ready to take on this question? Yes. Can I just hear someone to confirm if I'm audible?
You are very, very audible, more than the word itself.
Yeah, because I was wondering whether people are there.
You discover that there is only quietness. I think this question, if it was even tackled that time around. I don't think why people still have issues on the same.
Okay, I can see the raising of hands. Docs, it will help me to, I don't know, how do you check that someone has raised hand?
Just on the list of the participants, the first list that appears is the queue for those who have raised hands.
Okay. Mr. Brighton Mulenga, you can take it up, sir. Thank you so very much for coming aboard.
Oh, thank you. On this question, if I recall very well, what they did, the gentleman there, they just we just assume that since silver is a transition metal, we know how they behave. They've got varying oxidation numbers. They can have an oxidation number of either 1, 2, 3, and so on and so forth. So what we did here is we just find the number of moles of each element that we've been given here. After you find the number of moles, we multiply. Just assume that silver has got an oxidation number of 1. We multiply the number of moles by 1. Then we equate that number of moles multiplied by the oxidation number to the gold. Then the gold you multiply it with an x. An x simply means we are finding the oxidation number. I think that's what they did.
Okay, thank you. Any other contribution to what Mr. Brighton has just alluded to? I think that is a very good introduction of what we are supposed to do. Anyone to add so that we find each and everyone in here is able to find the state of God. According to him, he says that we need to convert the grams to moles. Then we find the moles of electrons, and those will help us to find the oxidation state. So from there, someone to add so that we move on. And remember, Doc Cyril stretched much of his time here and recorded a video and sent into the group. I'm sure that video was watched. So in short, what Mr. Brighton said, the whole concept here, we can look for keywords. Of course, we are taught that the same quantity of electricity was passed through these electrolytic cells, which means that if we had 5 amperes of current passing through the electrolysis that contains silver, it could be the same that was passed through the electrolysis that contains gold. So which means that these two are the same, and that implies that even their charges should be the same. So which means that here the concept of the equivalence of the charges is what is going to help us to find the oxidation state of silver. Of course, what he said, you can start with the one that you know that this one has a stable oxidation state, and that is silver. Silver does not change its oxidation state; it's always +1. So you write the equation, the reduction. How do you equate the half equation for silver? Okay, you balance it. You convert the mass of silver to moles. After that, using the balance equation, the half equation that you found, you're going to find the number of moles of the electrons that are needed to deposit silver onto the cathode. Then that you are going to find the charge, the number of charges of which we know, which is you just multiply the moles by 1 Faraday. Okay, and it will give you the moles, the number of charges. And since we have these charges, this side we end here. Now we go to the next part, which is silver. We do the same. The number of moles, that the grams of silver are converted to grams. Okay, and then again you come up with the balance chemical equation. We don't know the charge of silver, so it will be silver X plus the electron, and we don't know how many electrons are needed, so say X electrons to give you that is gold we're talking about, to give you gold. Okay, now we're looking for X. Okay, so you can simply write a statement so that you don't forget to say silver X, which is that the charge we're looking for, needs Xe, number of electrons to be plated. Hence, we're going to find this number of electrons. The way we do it, we multiply these electrons by the Faraday, 1 Faraday, so that we can have the charges. And since we have the X, so we're going to have X Faraday. I think that is what we're going to have somewhere there after we do whatsoever that we do. And then since now we have the charge from the other part and the charge from the silver, okay, the charge from the silver and the charge from the gold, you equate the two and then you solve for X, of which you're going to have the answer 2.994 or whatever that you're going to have. But here, if you round off that figure, you're going to have 3. I think that is the procedure that we follow there. For more information, this question was solved by Dr. Sililo. You can, I think you're going to find the link in the group. I think that's all that we are supposed to do on this question, unless there's a question and you need clarification so that we move on. Okay, Dr. Silo Muyunda, your mic is on. You can come in, sir.
Yes, please. Hello?
Yes, please, I'm able to get you.
Yeah, no, it is, let me just stop sharing the audio. It's just the audio of the other tab. Let me just close it. It wasn't like my mic was on, but it was the other tab. Oh, you wanted to ask something?
Oh, no. Would you just add on what we've just so far discussed on this question? Because I saw the video, you solved it in the group. Maybe you can also add some more. Maybe using, because we have so many ways of solving it. Maybe, are you in the state of maybe giving another way of solving it as that which you did in the group?
But I found that one to be the easier way. Of course, there is other methods that would give an equivalency of the mass and everything, but I'm not so confident with that way because the chemistry behind that method is a little bit questionable to me. Yeah, so I prefer using that same method, and even in the context of the question, it wouldn't be very wise to go in the equivalency mass to calculate the equivalence masses, but it would be very wise to use the already principles that we use in electrochemistry. And these are, of course, the ones we know for Faraday and everything, just like you explained. And unless maybe there is someone who would be not clear with it, I would still like share a little bit of clips of the videos of the video so that we can move together if at all you are remaining behind on that part.
All right, thank you. So I think you can do as you did last time. I think it's better that if you're able to send that video on the Sililoconnect YouTube so that they are able to watch it as well. Okay, the one that you just presented last time for for accumulation of knowledge anyway.
Exactly. All right, I'll do so.
I think that is clear more enough. So if you have a problem, the clip will be sent on the I think it could be on the mood on the Sililoconnect Moodle or on the YouTube channel, which is for Sililoconnect YouTube channel. You're going to access the previous video that Sililo presented, and even this vision that we are. I'm sorry, I'm not in the state of solving on the board, and I'm very far away from my board, so talking can do as we are doing here. So if you're not clear, just ask. You say, I'm not clear. What is the name of the YouTube channel? Dr. Cirilo, what is the name of your YouTube channel?
All right, let me just send the link real quick. It's just Sililoconnect. You search Sililoconnect, it's the first one to appear. If you search something like DME revisions, it's the first one to appear. Like, yeah. But just search Sililoconnect, it's the first one to appear. You won't get any other channel on the first list apart from it.
All right, thank you. Madam Lombe, what is your question? Madam Lombe, come on board. Oh, maybe she's gone.
Everything. I'm not connecting with what you're explaining in the question.
Okay. Okay, let's be together. I'll go slow and slow and slow so that you get it. So as I'm talking, you should be writing. Is that okay, Madam Lombe?
Yes.
Let me just help in Mukwa. Let me
Okay,
just help
sure.
in sharing the screen.
Oh, okay.
As yes. All right. So you start, then I'll be writing whatever you'll be saying.
Okay. Then Madam Lombe yourself, you can follow it that way. Okay. Are you able to rotate your screen now, sir? So that you is it rotatable? Are you able to rotate it?
I can. If I just
Okay.
rotate my.
Yeah. Even better. Okay. So the first step, we are given the masses. Okay, so that is for silver, we are given 2.64 grams, and then for gold, we are given 1.61. Okay, so
1.6 what? The mass for God?
you convert the masses. That is now for.
The mass for God is.
Let's start with
The mass for God is 1 point what?
the mass for gold is 1.61.
6.1.
1.
Okay.
Professor Akash, reduce your volume.
Okay. Thank you. Has it
Okay.
reduced?
So So we're going to convert the mass of silver to number of moles. Okay. So how do we convert that? We know what to do. And I think he's already written. So that is number of moles equal to mass over molar mass. So you do not multiply, but you divide. Mr. Kat.
Yes.
So mass over Mr. So that will be 6.24 grams over 107.86H2. 107.86H2. So when you divide, you're going to have the number of moles of silver, which will be 0.0245.
0 point what?
0.0245.
245.
0.025.
Oh.
0.245 rather.
All right.
So it's 0.0. This one.
So we are done there, and then you can give a summation on your own to say, okay, silver needs one more of electrons to be plated. That is after you've written the half reaction.
Okay.
I don't think so. You have to write the half reaction or what it is, which is silver
No.
plus. Should we write it?
No.
Okay. So, which means that the mole ratio is 1 to 1. So, even the number of moles of electrons is 0.0245. And now what we're interested in is the number of charges. So you multiply 0.245, that is 0.0245 times 1 Faraday. Okay. After doing that, you are going to have the number of moles. So the number of charges per se. So you can punch your calculators and get the number of charges. Anyone who has found it?
Two 2,361.5.
Okay, so that is that.
To the power what? If we round it off?
To the power 3.
Okay.
So this side we are done. We go to the next one, which is now God. Or rather, yeah, God. So you convert the mass again for God to the number of moles. So the same procedure follows. So I won't say anything you are going to convert on your own. So the way we did with silver, that's what we're going to do here. Okay. Yes, we've multiplied by the Faraday constant. So after I find the number of moles,
What have we found? I guess we're able to tabulate the value. I mean, for God.
8.17.
The number of moles.
Yes, 8.17 times 10 to the negative 3.
8.17 times 10 to the negative 3 moles.
Okay. Yeah. So now the next thing is to now use the same way we did with silver. That's what we're going to do here. Now at this time, I think it is imperative now to write down the half reaction.
Okay.
Yeah, so that they can follow it. So that is silver. On top we put X because we know the charge.
On top we put X.
Yes, as in
Okay.
representing the plus X electrons.
Plus
X electrons. Because we know that the electrons cancel that charge on top there. So if we've got 20 charges, then it means that we're going to have 20 electrons there. So equal to the God itself. So that is the equation that we're using there. That's the way we did it with the silver. So now we can see that the silver ion and the number of electrons that are in the mode of 1 to x. So to find the number of electrons, the number of moles of electrons, you multiply the number of moles of gold by x. So in short, we're going to have 8.17 times 10 to the negative 3 x as the number of moles of electrons.
We're going to have 8 point what? 8.17
8.17
times 10 to
to
the
the
negative
negative
3.
x.
Okay.
Have that, and we want the charges. So we multiply that number of moles that we've just found by the Faraday constant. So now it would be 8.17. That one multiplied by the Faraday constant. So the reason why we are multiplying now, what we are finding is the number of charges that were required for God to be plated. After that, you can write an acclamation to say, since the time was the same for both half reactions, then the number of charges should be the same. So we are going to equate the charges that we found under God to the number of charges that we found under silver. And then you solve for x. And that x you find is the charge of God.
Has
I think
somebody
that is
just
clear.
multiplied? Has somebody just multiplied this so that we write it? It gives me something like
It's this
771.
night.
Hello. When you multiply this, remember we had an x here. There is this x, which is supposed to be shown here. So when you multiply this, it's giving me something. I don't know whether my calculator is right. It's giving me something like 771.9 eggs.
Okay, so that is, I think, if at all, that is what you punch according to your calculator, then that is that. It's doing great.
For me, it's giving me
Okay,
788.
yeah, I think that is, my calculator is also giving me 788.
Let me just see the value. Oh, I see. I think I had made a mistake. It's 8.17 exponent negative 3 multiplied by 96.48.5. Yeah, you are correct. It has to be 788. Seven, 8, 8.
Okay, so now that is the number of charges under gold and the number of charges under silver we have, and we are told that the time was the same. So we can equate the two charges since the time was the same, which means that even the charges are the same. Okay, so we're going to have the charge 1 equal charge 2, that is Q1 equal to Q2, and the Q1 is that which we found under silver, and Q2 will be either way that you do it, it will still be the same. You solve for X, and that X that you're going to find is the number of oxidation state of gold. I think this is clear enough and more than clear. So also there's another method of which we cannot show here. You go on the YouTube or Sililoconnect. I think Mr. Silo will do the needful.
I have a question.
Yes, please.
Where you are saying that we can either use the oxidation state of silver as 2, 3. The process will still be the same, but here when writing the equation for the half reaction for silver, it will be 2 electrons instead. Then that's what can help to find the charge when silver's oxidation number is 2.
Come again, madam.
I still remember if I heard it now, or if I'm hearing it now, or I heard it last time. I still remember you said that because silver is a transitional metal, it can have an oxidation state of 1, 2, or 3. So does it mean that if I want to pick 2, the number when writing the half reaction, the number of electron will be 2 for me to go with a charge of 2, then following the same procedure?
I think you did not hear it from me. I think Doc Silo, you can come in on that one.
I haven't gotten the question clearly.
He says since silver is a transition metal, can we also pick on 2 as a charge and then we solve?
Oh, okay, on silver, where to pick on 2 as a charge.
At I left the meeting.
If it you left, yes. It would be it would give you. I'm not sure about that, but it won't give you a correct answer. It won't give you the correct answer. Yes, it won't give you the correct answer. Now, when you look at silver, let me see whether I can check the reduction tables. When you look at silver, it's in this case it's quite more stable if it has the oxidation state of 1, and that's the most favorable one. And let me just check reduction tables. Yeah, but that's the case.
So in short, when you're dealing with such questions, the most stable part to deal with it is to choose the oxidation state of 1 to the one you're comparing with. Right?
Yeah, the whole idea here is to pick the half. No, we are using the half reactions from the standard reduction potentials from the table. And if you check that table very well, it will be difficult for you to find the standard reduction, rather the half reaction for silver that has an oxidation state of 2. I don't think so. Anyway, I did not take much time to check if at all we have that on the standard reduction table. So I don't know.
Okay, I get it. I never knew that you were getting the equations from the reduction table there. I thought you were just making them.
No, we are getting them from the table.
Okay, thank you.
Sure. Madam Lombe, are you there? Lombe. Let's hope you're not a loser as well.
Not everyone can be a lousy, please. I'm here. Thank you very much.
Uh, these names are quite cumbersome to pronounce. Yes, Mr. Madam or Sir, yeah. Kombe, you can go ahead and you can help me on how you pronounce your name.
Okay, it's Combe Esperance.
Esperance, okay.
I'm not quite clear. Yes, I just want a bit of clarity on when we're doing the half reactions, like the one-to-one relationship. How what we doing it? The charge. I mean, like the number of electrons related to what?
But you know how to write the balanced half reaction, right, Madam Kombe?
Yes.
Madam Kombe, are you there? Yeah. So you simply write the
Yes,
balanced
I'm
half
still here.
reaction. Yes. So you simply write the balanced half reaction of that particular reaction you in this case for silver or whatsoever that you are finding, and you use those coefficients of the balanced reaction as your mole to mole ratios, and those are the ones that helps you to find the number of moles of electrons or silver, either way. So you simply balance you simply balance the half reaction, and using just as Mr. Akash is showing there. After you balance it, we know that for gold to be plated, it has to be reduced. And for it to be reduced, since it has a charge of whatever, if it has a charge of 20, for it to be reduced, it will need about 20 electrons. So that is what we did there. So you simply balance the half reaction, and then those coefficients will help you to find the number of moles of electrons or number of moles of gold. Okay, so that is what we call geochemistry part of this electrochemistry. I'm sure I think the steps will be sent in the group. If it is not in the group, the admins will actually try to find something and upload on the site that can help you to solve these kind of questions. Is that okay, Madam Madam Kombe?
Yeah, it's clear. Thank you.
All right, thank you.
You can call her Madam EK.
Oh, okay, EK. That's great. Question 6, due to outage of power supply from ZESCO. Mr. Muvita, are you in? Yes, he is even sharing. So when this man went to Ulozi there, he was posted after he finished his school, and there was no power where he was posted. Okay. And so we are saying due to outage of power supply from ZESCO, Muvita, a Lozi Unza student from Western Province of Zambia, decided to play around with galvanic cells and constructed a zinc copper battery operating under a zero resistant small light emitting diode, that is LED, at 25 degrees Celsius as follows. So given that cell notation there, I think you're able to see it from now. They're saying the mass of each solid electrode is 200 grams. Which of the two is a reducing agent? That's the first question that we need to answer. Anyone to come on board? Mr. Muvita? Oh, he knows Akash. Mr. Akash? Is he gone? Okay, Doc Cirilo, you can simply take it over a little bit.
He had gone. He had gone somewhere to
Yes,
inbox. was good.
Yes, please. Please go ahead and take it over a little bit. I'll be out of the class momentarily. Something just has just come up. Yes.
What
All
is the
right. Where's the question?
Question 6.
Okay. I'm seeing the, yeah, what is supposed to be done on question 6? Do you have anything down?
Yes, yes, yes.
Okay, Doxido, do you kindly scroll up a bit? We see what is down. Okay, wow, these are the questions. Okay, we are told that the mass of each solid electrode is 200 grams. Okay, B. Which of the two is a reducing agent? Okay, which of the two solids is a reducing agent? Now, if you look at this question, it's good that scientists, they take these things step by step and they don't leave anything. The same thing that you learned in the first topic, they've actually brought it again. Are we together? So there it's very easy. How do we determine a limiting reagent? Let's have someone to answer this from the audience.
Juicing.
What are you saying, Doc? I think you saying.
Juicing. You said limiting. Or maybe I'm reading with one eye. Then the other one. Yeah, it's reducing. You said limiting.
Me have said limiting. Which which of the
Yeah.
two is a reducing agent? Okay, which one is a reducing agent? We are looking at the basic key of
Doc Stilo, scroll down a bit.
Zinc.
I the question again.
Okay, somebody is saying, let me read. Let me read out what somebody said in the chat section. Zinc is a reducing agent. Is someone able to read this, the whole thing that Justin Charles, the doc, has written? Okay, so how do you, Doc Justin? Can you just turn on your mic and speak your answer? Hello, I'm in a library. Oh, okay. I see. Who is able to read what he has written? Huh? Doc Prosperous. Okay, let me read this in the chat section. Zinc is a reducing agent since it is causing copper to gain electrons. Good. A reducing agent is that which has been oxidized. Are we together? If something has been oxidized, it is that which causes a reduction on the other one. So they are saying zinc is the reducing agent since itself it has been oxidized and it has reduced the copper from copper to copper. Is that okay? It's clear.
Yes,
I was
and just
told
to add
silence
on,
means progress.
like
Yes, Doc.
I, on the what is cell notation, we can see
Yes.
like in the first place when you had zinc, then this other side is what zinc 2 plus. So when the oxidation state increases, meaning yeah, undergoing meaning it's a reducing agent, something like that.
Okay, something like that. Okay, cool. Something like that. Okay, so we know that oxidation occurs where? Oxidation occurs at anode, right?
Anode.
And oxidation occurs at cathode.
Anode.
Yes. So since it is occurring at the anode, we know that it is oxidation, and that which has been oxidized, it is it that causes a reduction, and that which has been reduced is what? Dr. Isaac, can you finish that statement?
Repeat what you said there.
Oh, I said that which is reduced. Okay, if something has been reduced, it is an oxidizing agent, and that which has been oxidized, it is
A reducing agent.
a reducing agent. Well done. All right. Dr. Silo, scroll up, we see the next question, which is B. We see B. All right. B is saying calculate the cell potential when this battery is first connected. Calculate the cell potential. All right. This is cool. So we have to calculate the cell potential. So the E cell here is going to be the E what? E anode minus what? Do you have anyone who is able to write this? Having seen the half reactions from the cell notation given there, we have to deduce that we know which one is oxidized and which one is has been reduced. Then we write the E cell, the overall. We find the overall E cell. This is what they are talking about on question B. Do you have anyone who is going to do that? Hello. Okay, yes, Dr. Justin. Is it Justin or Justina? Let me just check. Justin. Yes, Doc. Pick it up. Doc Justin. Okay, I'm going to write. Write, please. Write to Russ. And do we have anyone to check? Okay, yes, thank you. Yes, Doc. Oh, you are typing. How can I share my screen? Okay. You do you have a board? Okay. Here on the bottom, look at on the bottom, we've got this red button for exit. You've got the camera, you've got the mic. Now go to the far end where you have 3 dots here. Those 3 dots, Yes. You're already sharing your screen. Now, do you have a board in your phone? Like, do you have a board, a whiteboard, or any board that you use? Did you download it? You have to install it on your phone. Do you have it? May we have anyone to help Dr. Justin to share a screen, the one who has a board? Welcome, Miss Kai. No, I don't. Okay, make sure that you see to it that you download the board, Dr. Justin. We shall send you the link of a right board, or we shall just tell you what to download. Dr. Isaac, would you kindly help us to share the screen as Dr. Justin will be telling you what to write? Okay, Darlington is presenting. This is my name. You have to see me for a lollipop. So, Doc, you have to continue telling him what to write.
I'm not sure if it will work out because Doc Justin can't talk. He's in the lib, so I'm not sure if it's going to work out.
Yeah, this
There's
cannot
someone who
work
can
out.
talk.
If he is in the library, then it cannot work out.
Hello, am I logged out?
Okay.
Rotate your screen, sir, please.
Yeah, anyone to tell Doc Darlington what to write? Anyone to tell Doc Darlington what to write?
Let him rotate the screen first.
That you should write Tishani's name.
You want your name to be written down.
Okay, anyone to pick it up from there? Like the
Mr.
whiteboard is
Darlington, are you
there.
able to rotate your screen? Just rotate your screen so that, yes.
You can just turn on the like from the tray there up. You turn on the auto rotate exactly. Yeah.
It seems my board doesn't support auto rotate.
Oh, okay. All right. You can go ahead, of course, even in the portrait one.
Madam Prosper, please pick this question up. Is
For
Madam
finding
Prosper
the
here?
cell.
Yes, please,
Yes,
go
I'm
ahead.
in.
Okay, go ahead, madam.
Okay. So I'm checking the cell potential for zinc for the half reaction of zinc in the zoomed out book. I don't know, maybe someone has it so that we just continue.
It's 0.34.
Then you should be writing. It's what?
0.34.
0.34. It's a positive one, or you've already.
It's a positive.
What of for copper 2 plus this something?
Is
The other.
negative 0.76.
Okay. Considering that this reaction for zinc, it is from the beginning, I'm sure when this 0.3 something, what am I saying? I want to see for myself the what is the cell potentials. I'm not seeing this one for copper. You've said it's negative 0. The way they react, they have reaction for now because it will be copper 2 plus 2 electron giving us copper. It is negative 0.76. That's what we've said, right? Dr. Charles.
Yes, please, from the standard reduction potentials table. I haven't yet done the manipulation. I just gave it from the way direct from the standard reduction potentials.
I want to see for myself. Just a bit. Like,
You want to see the standard reduction potential?
yes.
Right, let me just share it up. I'm not
I'm
sure why
waiting
my
for
screen is
you.
not sharing. Um, not sure why it's not sharing.
Because I'm sure the cell potential, it is supposed to be negative. Now I'm shocked that this one for copper they're telling us it's negative. This one, which is already, which is the cathode one here.
We flip it, Doc. The presenter. If all are negatives, we flip the smallest.
Yeah, considering that this one for copper I'm thinking it's supposed to be a positive one. This one for copper, because it's the one which is big. This one for zinc, when you manipulate it, considering that according to how the equations come in the verses, it is a positive, then it's the one which is supposed to be negative now after manipulating it. So that our cell potential should be positive.
Look at the question, is it electrolysis? Because electrolysis would occur on both, whether negative or positive.
Yeah, it's electrolysis. I've seen it. So let me just continue now with the figures I'm given now that it's electrolysis. We are given,
Oh, good.
yeah, we are given the half reaction for zinc, giving us the zinc 2 plus 10 plus 2 electrons with a cell potential of, because before manipulating it, it was 0.3. Now that we've reversed it, it's negative 0.34. I don't know if you're writing what I'm saying. Then for copper, we're given copper 2 plus 2 electrons, giving us copper negative 0.76. So the cell the is equals to the cathode plus anode. The plus here works after reversing, like this one for zinc, how we've reversed it. Then when you write a plus here, cathode plus anode, it means that you get the figure which is already manipulated. If it's reversing, which is already reversed. If it was positive, the negative one. If the actual one was negative, then you're getting the positive one. So in this case, we're given negative 0.76 plus negative 0.34. Our answer will be negative. Let me calculate. 0.76. It's negative 1.1.
Dr. Charles, are you still in? Oh, Prof. Akashi, are you still in?
Right. Yes, doc. Okay. That was the question. Now, when you are dealing with electrolysis, you should bear in mind that the E cell, or rather the cell potential, would be negative or positive. Okay, because there is the inducing of voltage, rather the inducing of current to produce this voltage that we receive. It shouldn't be spontaneous only. It should also be non-spontaneous actually, and electrolysis. Now question C is, may I share my board now? Okay, Justin Chazia, share your board to solve question C. Question C is saying calculate the cell potential after 10.0 amps of current has flowed for 10 hours. This is good. Okay. Assume each half cell contains 1.00 liters of solution. So they want us to calculate voltage from 10.0 amps that we have, that is current. Then we have 10 hours of flow. Okay. So how do we go about this one to calculate uh, the cell potential? Anyone to pick it up? Hello. We are going to have the approach of moving from amps to, you know that is it coulomb? The coulombs, is it charge, which is given by amps multiplied by time. Okay. We move from that order, comes to Faraday constant in those orders. It seems to be silent. And the time is saying we are remaining with, it said what, 10:28. We are remaining with 3 minutes. I'll extend it to 10:25. Anyone to come on board? Doc Aphrodite. Oh, she's not in. Yes, Doc Darling. Doc Darling. Uh-oh. Mwami jindi janda huwa na chimwatupa.
Yanda kukwanena mwasika ama questions ongaye.
Tula question C. Pesita baribonye bantu.
Okay.
Yeah, we just
Oh, we
want
are on
someone
question
to
C
move
now.
from Sha.
We are on question C.
Yes, we just want someone to move from there. He comes to the charges. He comes to the Faraday things. We don't have people. Doc Lombe. Lolo. Please fill
Let
our
me
very
ask
mommy
a
thing.
question.
Sha.
Let me ask a question. When you find after finding the charge, then you go there to Faraday's where we are saying Q is equals to NL. What exactly are we finding? We are finding the value of N considering that Faraday is constant we have.
What are you saying? Let me. I didn't get you clearly. Is it Doc Prosperous?
I'm saying that when you find the charge, then when you use the charge to find the number of moles of electron, then we are using that number of moles of electron to find cell potential, or it's a question I want to know how to go about it. Maybe I can solve it.
Yeah, that's the way which seems to be simple. Or would people in the meeting have any other ways of going about this apart from that one?
Okay, anyone to solve this one, please, so that we move on. The time is. I don't know the set time by the. But
It's just 5 minutes. 5 minutes from now we are closing. At
okay, so
exactly
we really need to
10.
accelerate.
At exactly 10:25.
So, okay. Anyone who is willing to take on the question, I think we know the procedures.
Okay, let's do this. If somebody has failed to find the cell potential, let's have someone who's going to calculate the masses on D.
Are you? Which question are we on?
We are supposed to have C, the 10 amps
Okay.
current to calculate the
We
cell
can't
potential.
jump because you cannot manage to find the D if you don't find C.
Calculate the mass of each electrode.
So it's better we find C and then we get D. Is it D or E?
Yeah, I see.
Okay, yeah. If someone is able to find D, I think.
So somebody can find D without finding C, yes.
No, you can't manage.
Me, I can guess. Let me tell you the value.
Okay, sure.
The value is 22 grams.
Okay, so in conclusion, now we won't write anything, but we'll just give you the general steps, and then you're going to follow it, and you're going to answer on your own. Or better still, probably something would be prepared and be posted on the YouTube or on the site by the administration. But for the sensitivity of the time, this is how we can go about this question. We're given the current, which is 10 amperes, okay? And this is flowing for 10 hours, we know that. And we know how to find the charge. The charge is already found by current times time. Okay, or they can be called coulombs, equal to amperes multiplied by time in seconds. Okay, so after that we can find the charge given the time and the current. So you do that. I think you've already done that. So you multiply the current given times the time in seconds, and you're going to have 360,000 coulombs. Okay, that's the first thing that you do there. I think you've done that. You've written down. Okay, from there, the next thing that you do now is again to come up with the mole to mole ratio that will help you to find the number of electrons that are needed to deposit copper, or either way. Okay, so you're going to give an acclamation again to say copper 2 requires 2 electrons to be plated. Okay, you can do that. I think you can do that. In fact, before you go to that, we have we have the charge. So you divide that charge by 1 Faraday so that you have the number of moles.
Oh, the presenter in? Doctors?
Of electrons to be plated. Hence, you can find now the number of moles of copper that is plated out. So you divide the 3.73 by 2. Since that is the mole to mole ratio, that is 1 to 2, you're going to find 1.87 moles of copper plated. And then we know that the copper is reduced to copper, and that is on the, it could be on the cathode. Is it cathode or anode? Could be on the cathode. Yeah. So which means that copper,
Exactly.
the number of moles of copper will reduce by 1.87 for it to be plated, and we're going to have the number of moles of copper plated. I think you're following there. So you're going to say, since cathode lost 1.87 moles of copper ion and anode gained it, then from the cathode we're going to subtract that 1.87 moles to have the moles that remained on the cathode, and then the same 1.87 will be added to the anode to have the number of moles of zinc on the anode. So that is what we are going to do there. I think we've already done that. I don't know if there's someone who is left behind, but I don't think so. There's one who is left behind.
I am. I don't know why you've taken the number of moles you found after dividing Q over Faraday's constant.
So that is the number of moles of electrons, right? We are finding there. So for you to find the number of moles, yeah. So after you find the number of moles of electrons, after that is when dividing the number, the charge by the Faradays, you're finding the number of moles of electrons that are okay. After finding the number of moles of electrons, use the mole to mole ratio in your balanced half reactions, either for copper or the other one, which is zinc. It will still give you the same answer. So if we use copper, we know that copper has a charge of 2+. So you say copper ions need 2 electrons or 2 moles of electrons to be deposited. So since one mole of copper ion needs 2 electrons, then you need to divide the number of moles of electrons by 2 so that you can have the number of moles that belongs to copper 2. That's where we found the moles that I'm talking about.
Okay, thank you.
I think from there now we know what to do. Any question so far?
I think it's clear.
But in general, we're going to use the number of moles we are from calculating, right?
Yeah. Those are the ones that we are using now. So we know that copper is on the cathode, right? And zinc is on the anode. So copper will lose that certain number of moles that we are talking about, and then zinc will gain those number of moles. Okay. So what we are going to do is that we are going to convert this number of moles that we found for copper into molarity, since we are told that the number, the volume of the liquid is 1 liter. So we simply divide by 1 liter, we're going to have 1.87 molarity. They want to give you some moralities in the question there, okay? In the balanced whatever, I don't know if they were given in the question. There's some concentrations that were given in the cell notation. You can go upward, Mr. Cyril, just a bit, so that we see those that were given, the concentrations that were given in the, okay, those ones. So we're able to see that on the anode we have 0.1, and then on the cathode we have 2.5. So given the molarity that we've just found, which is 1.87, it will be subtracted from the cathode and it will be added to the anode. I think that is clear enough. So after that, now you can find the E cell. Okay, using what is that?
The nest equation.
The name nest. The name nest. Use the name test. Equation to find the E cell. I think no one is left behind here.
I think no, and you're out of time.
Unless chabe ngati mwenze mwagona chabe.
Unless mwingi obrosh.
No brosh. Okay. So after you manipulate the figures, I think you are going to find the answer to be plus 1.09 volts as your E cell after using those concentrations that we've just determined now. And then the same way can be done to their masses. You convert the moles that we just found, which is 1.87, to the mass. And then we're going to do the same. We're told that 200 grams of each. So we're going to subtract the grams. From the cathode, you subtract the gram that you calculate from 1.87 moles. And then also from the zinc, you subtract the same gram that you calculated from 1.87 moles, so that rather you add it. So from sorry, how do we do it there? I was saying
You
that
add where it has been deposited and you add where it has been removed.
exactly. I think that one is clear enough and straightforward.
Add and subtract.
Vizungu vinavuta vinabwera na ndege. So that is what you ought to do. But remember, you use 1.87 moles and the molar mass of zinc to find the grams of zinc. And then you do the same. You use the molar mass of copper to find the number of that are the grams of copper. Okay, those are the figures that we put there. I think the question is even finished. What will cause the battery to die after some time? All the zinc is consumed. So when the zinc is consumed, then the battery will die. And if all the copper too is also consumed, the battery will die. Or when the equilibrium is reached, which is the E cell of 0, the battery will die out. So those are that's how we ought to go about this question, the whole of it. Okay, unless there's a question. But looking at the time,